In today's module, we'll be looking at complex solubility equilibria. We'll be looking at how we can change concentrations in solution of things that are weakly soluble in solution by applying Le Chatelier's principle, by changing the pH of the solution. We're all going to look at these complex equilibria and what can be done to change those equilibria. Practice midterm and the study guide is posted. The midterm exam is Monday, July 20th. The exam will be 35, maybe 40 questions at most, multiple choice, short answer, fill in the blank. I will provide a periodic table of the elements and any equation and conversion factor that you would need. For the other summer session, I did a review session on Friday at our normal class time, 10 to 11:30. Let me know if that's something you're interested in. I can work through the practice exam then. I also wanted to do one review question from looking at pH and changing pH in the solution, just because this question from the homework was a little oddly worded. So the question states, how many units of pH increase will occur if 10 milliliters of a 0.013 molar sodium hydroxide solution is added to 90 milliliters of pure water? And to start this question, and the reason why I'm reviewing it, is we need an equation from first semester. When we looked at concentration first semester, we used an equation M1V1 equals M2V2. And all that says is the molarity of my first solution times the volume of my first solution equals the molarity times the volume of my second solution. And that's what we need to do because right now I know the volume and the concentration of sodium hydroxide. The problem is I add that to 90 milliliters of pure water. So I'm going to have a new volume after I add those two solutions together, and that new volume will also have a new concentration. So step one, I need to calculate what is that new concentration. So initially my molarity is 0.013 and my initial volume is 10 milliliters. I want to find what's my new molarity at the 100 milliliter volume. And I got the 100 milliliter volume from adding together the 90 milliliters of pure water with the 10 milliliters of the sodium hydroxide. So multiply and divide by 100. My second concentration ends up being approximately 0.0013 molar. So that's the concentration after mixing those two solutions together. That's my concentration of a strong base, sodium hydroxide. Well, now I know the concentration of my base. Now I can find the pH. But because we're given sodium hydroxide, I know the hydroxide concentration. Let's start by finding pOH, and then we can find pH. So we know pOH equals the negative log of my hydroxide concentration. So the pOH of this solution equals the negative log of 0.0013. So the pOH of this solution equals approximately 2.88. That's the pOH, and we are looking for the pH. So we know pH plus pOH equals 14. So if I rearrange this equation, I get pH equals 14 minus pOH. So the pH of this solution is 14 minus 2.88. The pH of this solution is approximately 11.11. So now for the last part, how many units of pH increase will occur? Well, initially, we started at a pH of 7 and we went to a pH of 11.11. So that change in pH, final pH minus initial pH, that change in pH is 4.11 pH units. Would be our final change in pH. And where did I get that 7, the pH of 7 from? right? We added that to 90 milliliters of pure water. So pure water is neutral because the hydronium and hydroxide concentration are equal. So the original pH was 7. I added a strong base to that. Strong base is ionized completely, so I could take the concentration of that strong base and use that to find the pOH and then the relationship between pH and pOH to find the pH of that solution and ultimately find the change in pH when those two are mixed together. Last class, we also looked at buffers and how buffers work. I want to review that as well because buffers are incredibly important. They're important to the pH of soil. They're important to the pH of our body, right? We have a buffer running through our blood right now that helps us maintain a stable pH. And so how a buffer works is we need to have a mixture of a weak acid and its conjugate base. And we need that in a buffer because if we have a weak acid present and we have its conjugate base present, if I add a strong acid to that, there's something in solution to help neutralize it. If I add a strong base to that solution, there's something in solution to help neutralize that. And that's what we have here. I've got acetic acid and acetate. So I've got a weak acid and its conjugate base. The important thing is, under basic conditions, here's my weak acid. Under basic conditions, I add a strong base. What happens? The strong base reacts with the acid, so that concentration goes down. The product of that reaction is more of the conjugate base, so that concentration goes up. The important thing, all of that strong base reacts, and so we only see a small change in pH. On the other end, I could add a strong acid to that solution, like HCl, and because I have the conjugate base present, the strong acid will react with the conjugate base, and so we'll see that concentration go down. The product of that reaction, right, if I add a proton onto the conjugate base, the product of that reaction is more of the weak acid, that concentration goes up. But again, the most important part is the strong acid reacts completely, and I see a small change in pH because instead of going to change the pH of the solution, the strong acid reacted with the buffer. So in a buffer, we need to have both a weak acid and its conjugate base present, and a buffer functions to help moderate changes in pH if you add a strong acid or a strong base. And so why is that important, right? So some of you may be familiar with the Adirondack Park, about 2 hours north of us from Syracuse. So in the Adirondack Park, acid rain is a really large problem. So for years and years and years, there's a high concentration of factories in the Midwest, in Pennsylvania, and for a long time, many of those factories, they burned coal, which produced acid rain in the form of sulfuric, right? The nitrates and the sulfates would lead to very acidic rain that, following the weather patterns, traveled to the east, creating significant amounts of acid rain for the Adirondack Park. And here in Syracuse, we're not that far away. So Syracuse is somewhere down here. We get the same weather that they get in the Adirondack Park. We get the same rain, precipitation, or relatively the same quantity of rain. And yet in the Adirondack Park, you can see examples of forest die-off because of the acidic conditions. You can also see examples of many of the lakes and the streams in the Adirondack Park are void of life. They're perfectly crystal clear blue lakes and streams, and yes, they look beautiful, but they shouldn't look that way. There should be algae, there should be lilies, there should be fish growing there, but because they're so acidic, right, nothing is able to live in those lakes and streams. And so why is acid rain a much larger problem in the Adirondack Park than it is here in Syracuse? And the main reason has to do with geology. So here in Syracuse, our main bedrock is limestone, which is calcium carbonate. And so if you've ever seen the Hall of Languages, those giant slabs of limestone that were used to build the Hall of Languages, the Hall of Languages is calcium carbonate. And calcium carbonate can react under acidic conditions to produce calcium, water, and carbon dioxide. So calcium carbonate is a great buffer, and that's why here in Syracuse we do not have issues with acid rain and changing the pH of our local soil, because our local soil is rich in calcium carbonate, creating a great buffer for that acid rain. Whereas in the Adirondack Park, the geology there is silicon dioxide. It's granite. Granite, no buffering capacity. And because there's no buffering capacity from the granite, the acid rain, it falls, it accumulates, it builds up, and eventually changes the pH of the soil and the pH of the lakes and the streams in that area. Whereas here in Syracuse, that calcium carbonate ionizes to give us calcium and carbonate, and that carbonate is a conjugate base of a weak acid, making carbonate a pretty good base. Because it's a good base, it can react with the acid rain, neutralizing that acid rain and keeping our pH relatively stable in this region. And so we're going to look at equilibria like that today. And so here are two examples of calcium carbonate, right? Stalactites, so coming from the ceiling, or this coral reef, both of those are calcium carbonate. We've talked about how calcium carbonate can be solid or it can be soluble depending on the conditions. So under acidic conditions, it can be soluble, right? And that's what we're going to look at, is how and where these equilibria can be established and what factors can influence these equilibria. Because certainly under certain conditions that we're looking at right here with the stalactites and the coral, certainly they can be solid, but they also can be aqueous in solution as ions. And so what do those equilibria look like, and what are some of the factors we have to consider? So most of the compounds that we've looked at are only slightly soluble in solution. And because they're only slightly soluble or nearly insoluble in solution, that means we can establish an equilibria, and we can think about determining these concentrations as an equilibrium calculation. So to start, we're going to look at how I would write these solubility products for these slightly soluble or mostly insoluble compounds going into solution. So in general, we have our generic solid Mx, where M is any metal and it's got its counter anion X. It would go into solution, right? It's a solid, it goes into solution, yielding M cations and X anions. So what would the equilibrium expression for something like this be? Well, the solid we can ignore. Solids don't show up in our concentrations for equilibrium expression. So my equilibrium would look like the concentration of products, so the concentration of M times the concentration of X. There are no reactants to consider because they're solids, and like all the different K values we've looked at this semester, we've looked at Kc, Kp, we've looked at Ka, Kb. This one is just Ksp. It's the solubility product constant, and it equals the concentration of the ions that I have in solution from that weak electrolyte, that slightly soluble ionic compound. So Ksp equals the concentration of M times the concentration of X in solution. Just like any equilibrium calculation, it always came back to what's the concentration of products over the concentration of reactants. And in this case, we do not have any reactants to consider because Mx is a solid. So a question for you, we've got this solubility equilibrium expression for barium sulfate. Barium sulfate goes into solution, generating barium 2+ and sulfate 2-. What would the Ksp expression be for barium sulfate? So the Ksp for barium sulfate, the concentration of products would be the concentration of barium in solution times the concentration of sulfate in solution. Both barium and sulfate have a coefficient of 1, so no exponents are needed in this Ksp. But the Ksp equals the concentration of barium times the concentration of sulfate. Okay, here's one more example for you to think about. We've got mercury 2 chloride. Mercury 2 chloride goes into solution, forming mercury 2 plus and 2 chlorides. The KSP for mercury 2 chloride would be what? Well, the KSP would be what's the concentration of mercury times the concentration of chloride. And because I have 2 chlorides for every 1 mercury 2 chloride that goes into solution, that concentration is squared. So KSP equals mercury times the concentration of chloride squared.